Hello everyone. This week we have Vaibhav from IIT Bombay. Vaibhav is a recent PhD graduate. His work is on, he will be talking about his work on limitations of massively parallel cross-time algorithms. I don't know, are you looking for postdoc positions?
Maybe this title is more to kind of make it so that more people are interested in this work, but it will more be about Boolean circuits. So I'll describe a little bit of motivation why we look at Boolean circuits. So let's first consider a sequential algorithm. What it will do is it will take some input x, do some instructions followed by some other instruction and get an output. While in a parallel algorithm, you have these inputs. You could in each layer compute some output, use that in the next layer, and again compute some output, finally get a single output. Now this layer could in essence be computed by one time step if you had many processors. So assume that each of these could be implemented on a processor, you have enough of them. Then this one layer would actually correspond to one time step. And this is essentially the motivation that if you had many processors, if you could actually design such an algorithm, then you could do that task much faster. So how we model it is via Boolean circuits. So here you have these inputs, and these are just logic gates and or not gates. So these are gates that many of you might be familiar with, but I will define them formally as well. So in a Boolean circuit, you take some inputs, you feed them layer by layer, and finally get an output. This will be one value, some true or false value, a logical value. And if you had enough number of processors, for each layer, you could use those processors to get the output, and the total amount of time will actually equal the number of layers. So this is why this is actually connected to parallel algorithms. Now, let me actually describe some of the Boolean functions that we can use in these circuits. So, for example, there is the AND function, which outputs 1, which is how we represent true. If and only if all the inputs fed into it are ones, which we represent for true. For OR, we have 1 if and only there is not all zeros. If there is at least one true input, then it's the OR function. Then this actually will be a very important function for us. This is the divisibility function with respect to some number n, which is 1 if and only if the number of ones in A, which I represent this by mod A. This is the number of ones in A, should be divisible by n. For example, if we have mod 2, then all it's essentially saying is that the number of ones should be an even number. So either 0 ones, 2 ones, 4 ones, so on and so forth.
So mod 2 is 1 if mod 2 is 0.
That's true. This is actually kind of a negation of it.
But if it's not divisible, it's 0.
Yes. So this is a Boolean function. It's a logical function. So either true or false, 0 or 1. So the majority is 1 if and only it has more ones than zeros. So ones should be in the majority. So this is just like a voting function. If you have more votes for a candidate than for the other candidate, that candidate wins. So ones should have more votes, you get the majority function. And then there are these functions which will be helpful for us, which actually correspond to how many number of ones are there in the input. If there are w many ones, this function is 1, otherwise it's 0. So these are some of the constituent functions that we are going to use. Now, one property of these that will be useful for us later is that these are symmetric functions. What I mean by that is that if there are two inputs which have the same number of ones, which is also called the Hamming weight, if they have the same number of ones, then the function outputs the same value of those two inputs. You can see all of these are symmetric functions. The problem that we are going to look at, so first let me show you an example of how we can use these functions to construct some other function. So I have a circuit here, an OR taken over 3 ANDs, which take x1, x2, x3 like this. So can anybody guess what this function is computing? What is the function computed by this circuit? Majority. So if somebody has seen perceptrons, like this is very common construction using ANDs and ORs, and it actually computes the majority function. Sum of xi should be more than 1. But if I wanted to extend this construction to more number of inputs, so let's say you have 100 inputs or 1000 inputs or n number of inputs in general, then you would need many gates in this construction at least. But what we know is that if you only use ands and ors and nots and the number of layers were a constant, this is very important for us. The whole theme of this is when the number of layers is a constant. If the number of layers are constant, you are only using ANDs or NOT gates, then you will actually need a large number of gates, which is like some exponential in the number of variables. This is large for us. You will need a large number of gates to compute the majority function. What we are actually trying to answer through our work is a conjecture by Barrington in 1989, so it's like 35 years old at this point, which is that if along with AND or and NOT, you also allow, say, the mod 6 function. So the number of ones should be divisible by 6. If this were also allowed, even then you cannot compute the majority function with constant x, which is the number of layers, and polynomially many nodes, which corresponds to the number of processors in our model. So what we are essentially trying to prove is that even if you are allowed these operations AND, OR, and mod 6, you will still not be able to compute the majority function. And in fact,
there's one thing, unless someone misunderstands, is you're also the way you've done running the circuit so far. I mean, for that, it's important that you are also allowed to take as input not of a.
Yeah, so not is missing here. Not as a gate itself is allowed.
Okay, or you can assume that the not of the variables are allowed.
That is also fine. But in fact, what he points out that mod 2 is true when mod 2 is not true, that actually allows you to implement not using mod 6 too. So it's not technically necessary, but yeah, you should allow to use negations of the variables as well. So yeah, so the conjecture is that if you had a constant number of layers, you would need more than polynomially many nodes to compute the majority function. So now,
and just for those who are this one here, the fact is the important thing is 6 is a composite number.
Okay, yes. I actually want to come to that a little bit later. Yeah, but yeah, so what I'm saying is here you could actually use any natural number m, but the important thing is it should not grow with the number of inputs. So here the number of inputs is n. This m should not depend on n. So you can choose to use 6, you can choose to use 10, you can choose to use 20. But yeah, what Prahlad is saying is that if you actually allow it to be a prime, so you will see that that is already known. For that, we already know. So now a little bit of characterization as well. So if we look at all circuits that we can form, which have a constant number of layers, and where we are allowing these gates and or mod gates, and we look at all the functions that this circuits can compute, this set of functions is called ACC0.
In polynomial size.
Of course, in polynomial number of nodes and constant number of gates. Polynomial size, constant. This class is called ACC0. So, okay. Now here one thing you might notice is that as you change the number of inputs, so let's say you had 10 inputs, but now you want something for 100 inputs. This construction that I give to you could be different. Okay? If you had 10 number of inputs, you would use some construction. And then when you increase the number of inputs, you can change the construction to allow some other kind of circuit. All I am asking for is that the number of layers should remain a constant and the number of nodes should grow as a polynomial. But you could keep using different circuits. Now this is called non-uniformity. And non-uniformity actually allows you more power. While when you think of something like an algorithm, in an algorithm, the number of steps that you have is actually already written. It does not matter how many inputs you get. You will say that, okay, this is the first step, this is the second step. They might be repeated some number of times. but the number of steps is fixed. It is a constant. While here, this can actually keep changing. So this gives us a bit of a weird power. So we first want to understand how do these circuits correspond to the natural notion of algorithms that we have in our mind. So let's try to understand that. P, this is usually the class which is mostly studied in algorithms, in which we have polynomial amount of time to compute the function whichever one we want to compute. For example, you want to find what is the shortest part between two nodes in a graph. This is a problem in P. A very famous problem which required a lot of effort and proved by Agrawal, Kyle, Saxena is that if there is a number, we want to determine whether it is a prime or not. That is also in P. So you can actually do this by an algorithm in polynomial amount of time. Now this is actually contained in a class in which you are allowed polynomial amount of time, but just to verify the solution. Somebody gives you the solution, you just have to verify it. For example, you are given a number and you are given its prime factors. You can multiply them and check that this prime factor actually gives you this number. This problem is in NP. For example, another question is, given a graph, does it have a Hamiltonian cycle which visits all the vertices exactly once? I can give you a cycle, you can verify it, but we do not know if we can actually find such a cycle in polynomial time. So we have class NP, then we have a much bigger class, which is actually provably much bigger than P, where you are allowed exponential amount of time to find the solution. And then we have another class which is bigger than NP, where you are allowed exponential amount of time to verify the solution. So you could be given some problem, you get an exponential amount of time to verify what the solution of this problem is. On the other hand, we have these classes. So this AC0 is the class of constant depth circuits, just like we have been studying, but you are only allowed AND, OR, and NOT gates, for which we already know that there are many functions that this cannot compute via a list of works. So this is a very old stuff. I mean, important, but old, as it has been established for quite a long time. Then even if you allow mod P functions, where P is a prime, 2, 3, 5, whatever, even then we know via two works of Smolensky and Rasborough that this cannot compute the majority function. Now, one thing about majority function you will notice is that it is actually in P already, right? You can just very easily sum up all the inputs and find out whether the majority holds or not. Right? But for ACC0, where you are allowing a composite modulo, for a long time we had no idea what to do with it. Like we did not even know if a problem in non-deterministic exponential time is not in ACC. I mean, it could well have turned out to be that this very big class is in this potentially small looking class. So it took a breakthrough by Williams in 2014 to prove that this indeed is not the case. And this was actually a major result. So it kind of highlights the difficulty in trying to prove lower bounds against even these small circuit classes, which have just a constant number of layers and polynomially many nodes. But what the conjecture states is that there is even a much simpler function, which is in P, majority function, which is not in ACC. So you can kind of already understand that if this took a breakthrough, then trying to prove it for the majority function will probably require much more effort. And the hope of this talk is to get you interested into the fact that, okay, there is already a little bit of progress toward that question. So maybe if more people put effort into that question, then we may actually be able to resolve this. We do not know how long it will take. Maybe it will take another 20 years or maybe just 2 years. But hopefully it can be solved.
The class you're working with is not ACC0 because you only allow counters for one modulus, right?
Yes, but if you allow it for a constant number of modulus, that is also fine.
No, not constant numbers. You're giving union over all possible error, right? Union over all.
Of course. But even in one circuit, if you allow a constant number of moduli, that is also fine. That is also in ACC0.
So
That's an example of an ACC0 circuit.
Huh.
The class ACC0 is the union over order.
Achha, of course, yeah, that's what you meant. Yeah. So you're allowing any modulo m, but
So you're not showing that even if you're able to show the thing about majority, it won't say that it's not an ACC0. It will say that it is not in the subclass.
why?
Because
We are saying that for any modulo it will not work.
yeah.
And ACC0 is the union of all of them. So it is
But
not.
But the ACC0, I thought it allows different modulus for different rates. We can have.
If you only have constantly many showing up in a circuit, you can simulate all of them with the modulus corresponding to that LCM.
Why would there be polynomial?
I mean, yeah, but polynomially many, but they are all supposed to be, I mean, the different moduli are not supposed to grow with the number of variables. So which basically means that there's only constantly many that's showing up.
I see.
So that's what I'm saying. So you are allowed to use different moduli in one circuit, but none of the moduli should grow as the number of inputs, and the total different number of moduli that you are using should also not grow as the number of inputs.
Which is the same as just using one moduli.
Which is the same as just using one moduli.
But you get to, for every circuit, you get to pick which moduli.
That's right.
For every circuit class.
For every-
Yes.
No, given a problem.
Given a problem, yes.
You might pick a particular modulus and then that modulus.
Then it has to be used for each input size. So it should just not change with the input size. That's it.
Yeah.
That's it. So yeah, so and then there is this big class, which is the class of all polynomial size Boolean circuits, P/poly. And the hope of initially studying this class was to prove that NP is not contained in P/poly, while any polynomial time algorithm is also a polynomial size circuit. So that would already prove P is not equal to NP. But I do not know how close we are to this, and I would say we are probably not even epsilon close. So this will probably be a much harder problem. Yeah. So now, how would one try to prove such a statement? And in fact, we can even look at the proof of these statements and try to understand what kind of methods have been used. And a very successful method is actually based on polynomials. So the conjecture we are trying to prove is majority is not in ACC. And polynomial representations of Boolean functions, also called the polynomial method, has turned out to be really useful in the study of Boolean functions. For example, you could ask that, okay, on all Boolean inputs, the polynomial should match the value of the function. Now, this is very well understood, and if somebody has done a little bit of logic, then they might be able to figure out using the main terms of f that how to construct such a polynomial. This turns out to be unique, and yeah, so very well known, very well studied.
Well, polynomials, what's the underlying field you're talking about?
So right now I am actually trying to gloss over those details.
Okay, fair enough. Okay.
But in some places I will talk about this. So for example, another notion you could ask for is that, okay, let me not be equal on all points. I am allowed to deviate from it a little bit. So P approximates F. PA and FA are closest real numbers. Right? So if F is 0, then P is allowed to be, say, minus 0.1 to 0.1. F is 1, then P is allowed to be from 0.9 to 1.1. This is another notion of approximation. This is very well studied, has lots of connections to learning theory, to quantum complexity, to cryptography, secret sharing schemes, and many more. So this is just one of, it has actually turned out to be just a sub area in itself, the study of real approximations. So this itself is very interesting on its own. Another notion of approximation is that you have a distribution of polynomials, not just one. You have a distribution of polynomials, and for every Boolean point, a randomly chosen polynomial will be correct on F with high probability. So with 0.9 probability, a polynomial that you choose will actually give you the value of that. So this is another notion which is again very well studied and also was studied by Vaibhav and Smolensky and was actually kind of pioneered by Vaibhav and Smolensky. And quite a lot is also known here. But if we wanted to use them for understanding something about ACC, then what we know is that even the mod 6 function, which is in ACC window, already requires high degree in all three modes. So if we wanted to use the fact that such approximations exist, for mod 6 they do not exist. How would generally one try to use the polynomial method? They will say, look at this Boolean circuit, I will find a low degree polynomial for it. And I am trying to prove majority cannot be computed by such a circuit, so I will prove majority does not have a low degree polynomial. And that will prove what I want. But even mod 6 requires high degree polynomials here. So these notions will probably not help. What might help is torus polynomials.
But mod 2, for example, will not have, has a low degree polynomial?
Mod 2
Yeah.
over F2 it does.
So not
Of this type. Third type.
over F2, it obviously it can just do it exactly.
Yeah, of course. So yeah, of course you can do it exactly. Yeah.
But over the reals.
Over the reals, no.
So, but we're able to show lower bounds for mod 2. And why is this?
So that actually happens through other models.
Okay.
Yeah. So in fact, the fact that mod 2 does not have low degree real polynomials helps in proving that mod 2 cannot be computed by a class of circuits.
Yeah.
Right.
Yeah.
And in fact, mod 6 requires high degree, helps us in proving that AC0 with mod P gates cannot compute mod 6.
Sure. Yeah.
Okay. So these have turned out to be helpful, but it just seems to be the case that they will not be helpful in this case for the question that we are trying to answer. And what might help is torus polynomials, which was a model proposed by Bhrushundi, Hosseini, Lovett and Rao in 2019. So we start with a polynomial with real coefficients, and we say that it approximates a Boolean function within some deviation epsilon if there exists some integer, and how we will use this integer is that px is allowed to be this integer plus the value of the function plus minus epsilon. So it's allowed to stay within this range. For example, if f were 0 and let's say epsilon is 0.1, then p is allowed to be from minus 0.1 to 0.1, but also from 0.9 to 1.1 and also from 1.9 to 2.1 and similarly on the negative side. So it's allowed to fall in any of these small intervals. There are many small intervals and p is allowed to fall in any of them. And similarly, if f were 1, then this half would say that you are allowed to be from 0.4 to 0.6 or you are allowed to be from 1.4 to 1.6 and so on and so forth on either side. Right? So what it is essentially saying is if f is 0, p should be close to an integer. If f is 1, p should be close to half plus an integer. This is the model of computation that we are studying. And why is it called torus polynomial? Because there is this wrap around that is happening, right? The integer does not matter. So 0 gets mapped to 1, also gets mapped to 2. So it actually becomes a torus. That's why it's called a torus polynomial. Now, if such a polynomial exists, which has certain degree d, and if it satisfies this condition, then we say that the error of p with respect to f is epsilon. So we are trying to understand for which functions such a polynomial exists, which has low degree, and for which functions it does not.
Sorry, sir, just silly question. You said it's called torus polynomial because there's a wraparound.
There is a wraparound.
Why is it not just the full polynomial? Torus polynomial should be two wraparound.
Yeah, so I mean, circle is kind of is it a one-dimensional torus? I think circle is a one-dimensional torus, right?
I would normally not think of a circle as a one-dimensional circle. But this is similar to basically saying that you want the fractional part of P of A to
Yes, exactly.
basically tell you what
F is, yeah.
what is.
Yeah.
So fractional part of P should tell you what F is. Yes, that's exactly true.
Yeah, but I don't have an answer to
Could have
I
been
don't know why
called-
by the terminology.
No, because I think you can assume that all the x1 to xn are not real numbers, but are all coming from 0, 1 to the.
no, x1 through xn are coming only from the Boolean.
Oh, they are only coming from the Boolean.
Yeah.
So
You're just computing the value and then just dropping the integer part.
So
Yeah,
maybe
mod one.
torus.
Yeah, mod 1. So then torus is just the fancy.
Yeah, so it could be because of the way that this actually comes about. So the motivation for this comes from higher order Fourier-analysis, where they studied something called the torus, which is just R by Z, which is called the torus in that literature. So I don't know why it is called the torus again.
But traditionally, they are called the circle. Circle, vector, etc. They were all.
Yeah.
Oh, okay. So okay. So then I
At some
really
point,
want.
This is also part of appealing to a larger.
Yeah, that's true. I mean, yeah.
Yeah.
Yes.
Yeah, okay. So yes, so I actually just wanted to give a small example. So for example, let's say we're trying to approximate the mod 2 function. Then we just look at this polynomial, which is summation xi plus 1 by 2. So you can see that on the all 0 points, p is half and f is supposed to be 1. So this is half, this is 1, this is 0. So you can see that when f is 1, it is close to half plus an integer, and when f is 0, it's an integer. And you can see that the error of this polynomial is actually 0. So the mod 2 function is an easy function for this. And what Bhrushundi, Hosseini, Lovett and Rao proved is that if you have, say, a function in ACC0 which has, say, depth 10, so number of layers is 10, then there exists some polynomial p of degree, say, log to the 100. Maybe this is not correctly exactly 100, maybe 1000 or 10,000 or whatever, but it's some constant, such that the error will turn out to be, say, 1 upon n square. So you have a depth, you have an error for which you have a corresponding degree. In general, this could be some constant, this could also be some constant, and this degree will turn out to be some constant power of log. So in general, when we study the approximation of Boolean functions, this is what a small degree for us means, that it should have logarithmic, polylogarithmic degree, some polynomial of logarithm.
Just to take away is any ACC0 thing is well approximated
Well
by these
approximated
torus or something.
by a low degree.
By low degree.
Low degree. Yes. And yeah, so what we would like to prove is that for the majority function, there is some constant such that if you wanted to approximate it by small error, then you would need large degree, at least faster than any polynomial. Any polynomial. So now, how would generally one prove such a statement?
The conjecture made by BHLR or
So they make a much stronger conjecture,
okay.
which we do not hope to prove.
So do you believe in them?
Actually, not really. We believe that, okay, so the conjecture may be true, but what we believe we may be able to prove is much weaker.
So, sorry, so one thing. So we do, I guess we don't know of a function which has a low degree torus polynomial approximation and seems unlikely to be an ACC. Do we have it now?
Oh, yeah, so we do not have that. So what you
For all we
essentially
know is that this conjecture might be equivalent to Barrington's conjecture.
that will as well be the case. Yeah, I actually do not know. So basically, what you are asking for is separation between ACC0 and low degree torus.
No, we cannot unconditionally separate it because then we would have need a lower bound for ACC0. But I'm just saying, we have not been able to come up with a polynomial function which plausibly be able to be out of ACC0, yet has a low degree torus polynomial.
Mhm.
Yes.
So there might be something like some promised majority or something which is not in ACC0 but has low degree torus polynomials, but I'm not really sure. Not really sure. Yeah. So yeah, so now sure, we have some conjecture, and if we do not have a proof approach, then why would anyone be even interested in trying to approach this conjecture?
So this conjecture implies Barrington's conjecture.
Yes.
So, but what's the upper bound known for
Torus
majority in terms of torus polynomials? What's the degree? How large degree is required? N or root n or?
we do not know. So the best that we know for majority for torus polynomials is actually via real polynomials. For real polynomials,
Square root n.
no, that's order n.
Order n. Yeah.
Yeah,
But wait a second, so,
upper bound in terms of upper bound, I'm saying.
so sorry, so there is this upper bound, yeah, upper bound, but we, for example, we know that square root of n
Mhm.
times polylog n, whatever. That degree is enough to approximate the majority function over
Torus polynomials.
no, modular polynomials, right? Like mod 2 or something. Yeah.
Oh,
There
I
is certain-
see.
Now, can't you convert that to by an averaging trick to a torus polynomial?
That might very well be the
I mean,
case.
in fact, that's a probabilistic polynomial, so I would think that would be very good.
Yeah, I would.
What I said, like, you might have majority might have an upper bound of square root.
Square root of
Yeah,
n.
yeah.
Yeah, I would think that
Well,
square root
well,
of n upper bound exists.
Square root and polylog something. like
Yeah,
that.
ignore it.
Yeah, that might actually work. You're correct. Right. So yeah. So the main thing that we are actually going to try to do here is that we are going to write a linear program to try to prove this conjecture. So let's say that I want to prove that there is no degree 1 polynomial which approximates the majority over 3 variables for certain errors, say 1 by 10. I hope this is visible, it's not too small. So yeah, so what you will get is you evaluate it all 0 points, you get alpha 0, and you write it as a linear constraint. That alpha 0 should be within some z1 minus 1 by 10 to z1 plus 1 by 10, where z1 is an indeterminate. I do not know what this integer is going to be, but it's just 20, that's all I am. Similarly, for 1, 0, 0, I get a linear constraint, and I get a bunch of linear constraints for all Boolean points. I am going to collect up all these linear inequalities and write it as a linear system. So we have some function, some error parameter, some d, and for each plausible values of these integers, I am going to write a linear program. For example, in this case, this is the linear program. So what I have done is I have so this is only for so this is only for 2 variables. Sorry, this x3 should not have been here. This is only for 2 variables, x1, x2, and this is the corresponding linear program that I am going to. This should have been less than equal to. It's not equal. Okay, so there are 2 typos here. This is only x1, x2, and this is less than equal. So if I am trying to prove that there does not exist a polynomial, I am essentially saying that there do not exist such coefficients which can satisfy this linear program. So it's essentially I'm saying this linear program is infeasible. But proving things are infeasible, like generally tends to be hard. In many mathematical themes, proving things are infeasible tends to be hard. Like how do you
More
prove
than
it not
two
right?
cancels, right? Because all of these should be plus. All the minus 1 or 10 should be plus probably.
Yeah, this is also a type. There are 7 types, sorry.
6.
6 types.
That's okay.
Yeah, exactly.
I'm counting.
So yeah. So it's a good catch actually because it's very important that these are all pluses. It's a good catch. So yeah, so what we are trying to prove that this is infeasible, but that's generally very hard to do.
It's linear program. So you have clarity.
Exactly, and that's what we are going to do. Yeah, so we are going to prove that these all programs are infeasible using the dual polynomial method, which lets us convert this to the dual. So you treat the coefficients of
Except
polynomial.
the tree is not quite the usual, I mean.
It's not good.
Instance of the z function gives you a linear.
Yes,
program.
so that's what I'm going to
Yeah.
say. So for each combination of z's, you actually get a linear program And all of these linear programs should be infeasible for me to prove that there does not exist a torus polynomial approximation. And what Farkas lemma tells us is that if this is infeasible, this is feasible and it is an equivalent statement. So now what we are essentially trying to prove is that for all possible values of z, these programs are all feasible. So this is what our objective is now at this point. So we have to satisfy these three constraints to try to prove our result. Right. Okay, so first thing that I would like to talk about is just these two constraints. So you have A transpose beta should be 0, which is essentially saying beta is in the null space of A transpose, and beta should be non-negative. So this is something that some of you might have seen is called a polyhedral cone. So what it is essentially you have a bunch of rays, finite number of rays, and you are taking the convex hull of them. You get a polyhedral cone out of it. And to understand the polyhedral cone, it's essentially the same as trying to understand its extremities. But that's not something that we were able to achieve. It turned out to be very, very hard. So we actually have, even at this point, we do not have many ideas on how to get those extremities. But we did notice something, which is that this A transpose actually looks like one matrix followed by its negation. For example, in this case, A transpose is nothing but this. You can see it's this matrix followed by its negation. So if you have a vector in the null space of M, and you form two vectors using the positive and negative entries like this. So 1 goes to 1, but minus 1 goes to 0, and similarly 1 goes to 0, but minus 1 goes to 1. This is formed using the positive, this is formed using negative entries. And you append them together, you will get a vector like this in the polyhedral. So instead of having to work with a polyhedral cone, which we felt is very hard to do, we actually only have to work with a null space, which is now a linear programming object. Also, if you have a gamma from which you get a beta, then this expression B transpose beta turns out to be just the inner product of gamma with z plus f by 2. So z plus f by 2 is also a vector, gamma is also a vector. Just take the inner product. So this is also a type. This is 2 to the n. Okay. And here there is another term which is the L1 norm of gamma, which is the sum of absolute values of gamma. So this is the expression. Yeah, so how does that help us? Done a lot of calculations, but none of this at this point seems to help us. So we have to, for each gamma, we have to find the gamma, for each z, for each possible values of z's, I have to find the gamma in the null space, it satisfies this constraint. So now let's consider the following quantity, which is take the minimum over all possible z's. For each z, find the gamma which takes the maximum value of this. Then you know that this goal is achievable for any epsilon less than epsilon naught. So if I take any epsilon less than epsilon naught, it doesn't matter what z I choose, I can always find the gamma such that this quantity will turn out to be negative. This is a very simple, straightforward calculation. So one possible solution is, of course, to study the extreme ways. And in linear programming, they are also called the basic solutions. So you can think of it in either way. But again, as I said, this we did not find easy. So the approach that we are proposing here is projection based. So we are thinking of it in a bit of geometric terms. So we are saying, let's project z plus f by 2, this vector, on the null space of M to get some vector gamma z. As we are projecting, it's guaranteed to be in the null space, like just by its definition itself. And it achieves the maximum value of the inner product divided by the L2. Right? Because that's what the projection is by definition. It achieves the maximum inner product divided by the L2 norm. And we also know that the L1 norm cannot be much larger than the L2 norm. And we also know that z plus f by 2 gamma z is nothing but the norm square. So this is so many types. This is supposed to be gamma z. because projections are idempotent. So the inner product with the projection is the L2 square of the projection itself. So what this helps us to prove is that epsilon naught has to be at least the L2 norm of gamma z divided by 2 to the n by 2. So if indeed we are able to prove that let's say there is some C for which the following holds, that you consider this matrix M for a D which is log to the power some constant, and for any z the projection satisfies this criteria, which is that the L2 norm is at least 2 to the n by 2 upon n to the C. Then by all of this calculation that we have already done, we can see that the error has to be at least 1 upon n by C. So the key takeaway I would like for you to have from this talk is that there is this whole like line of works which are trying to prove something about ACC 0, that majority is not in ACC 0, and what we do is convert it to a question of trying to prove something about the projection. Now, this conjecture about the projection is not necessary for proving something about torus polynomials, but what we are showing here is that it is sufficient. If we prove this, we have a lower bound for the torus polynomials, and we prove that majority is not in ACC. Now, this is not yet it. Like we actually have some calculations for this projection matrix also. So what we prove is that the projection matrix for projection on null space of M satisfies this recurrence relation. So if you have N and D, you can get the projection matrix for N and D using N minus 1 D and N minus 1 D minus. This is kind of like a binomial type recurrence in which N minus 1 D and N minus 1 D minus 1 give you the matrix for N D. And there are some base cases. Pn minus 1 is just the identity matrix. P10 is this J type of matrix, but with signs. And we also do some calculation to actually get it. Okay. Yeah, so this matrix P and D is of size 2 to the n cross 2 to the n, and its rows and columns are indexed by all subsets of 1 to n. So you have 2 to the n subsets, that's how many rows and columns you have. And for two subsets S1, S2, we can actually tell you what the entries of this matrix are supposed to be. If they are equal, then there's this partial binomial sum, and if they are not equal, there's this ugly looking partial binomial sum. It's yeah. But if any of you want to try and attack this problem, like I'm quite happy to let you do that. So we have an explicit matrix. We are giving the actual entries of this matrix, and what you have to try to prove is that for all z for a given function, the projection of z plus f by 2 using this matrix will have large L2 norm. And even if, let's say, you are not able to prove it for all z's, let's say you are able to prove that for a very large family of z's, the projection will turn out to be large, then it actually helps us already, because then for those other z's, we might try to find some extreme ways and try to find some other method to rule them out. So all we are saying is that this is one potential approach to try to solve the problem. Yeah, so this is the reformulated conjecture. Consider an integer vector with entries indexed by subsets of 1 to the n. All entries for sets of size more than half are odd. This corresponds to the majority, because majority gives us a 1 by 2. So you multiply it by 2, you get an odd integer, and other entries are even because majority is 0 there. And for any d, the projection is going to be large. That's what we have to try to do. So now this is just some approach that we have proposed to try to prove something, but we also have some results, but that's in the context of symmetric polynomials. So yeah, so there is like some small implication I want to talk about. If somebody were able to prove this lower bound for torus polynomials, it actually has some interesting implications for the next frontier of Boolean circuits, which is related to this class called TC0. So in ACC0 we had these functions, which is OR, and mod and gates. In TC0 you allow the majority function itself and the NOT. So you are allowed to use the majority function in any way you want, constantly many layers, polynomially many nodes, and this is called TC0 class. And for this, we do not even know if any XP is contained in it or not. And one of the next frontiers is to try to prove any XP is not contained in TC0. And there is something to be said about the proof techniques itself for such a statement, which is that if there was such a proof which is computable, right? That I give you a function which is all the evaluations of that function, truth table of the function, and you can tell me that this proof applies to this function, and it applies to a vast majority of functions. Then it's called a natural proof. Natural in the sense that okay, it's very easy to compute and it will hold for most functions. So let's say somebody gives you a technique to prove that some function is not in TC0, which you can actually implement as an algorithm and it applies for most functions. It's called a natural proof. And if you prove that majority is not in ACC0 using torus polynomials, what you will prove is that no ACC0 natural proof can exist against TC0. So any proof which is showing that some function does not exist in TC0 can be simultaneously computable and applied to a vast majority of functions. So this is an interesting implication in the sense it tells us something about the method of proofs itself. That okay, if you are trying to prove such a statement, then you better not try to prove it using an ACC0 natural proof, because it cannot work. Now, okay, so this actually follows from a work of Chen, Lu, Liu, and Oliveira, as well as of Bhrushundi, because that's the original work. So it actually requires two works to get to this implication. But what we are essentially proving is that if majority is hard for torus polynomials, then some kind of techniques for trying to prove something is hard for TC0 are ruled out. They cannot work. So we better not try to use them. Now we also have some results for symmetric polynomials, but I do not think I have a lot of time. So I'm not really going to go into the proof. I'm just going to describe the results. But how much time do I have? 10 minutes. Okay. Okay. So I'll just try to take 5 minutes and wrap this up. So one thing I noted about the the Boolean functions that we were studying is that they are symmetric, which is that on functions with points with equal Hamming weight, they gave the same value. So now we might ask that okay, what if our polynomials are also symmetric? And in this case, it turns out to be equivalent to saying that okay, of course, the original definition of symmetric polynomial itself is that all monomials of same degree should have the same coefficient, which is that if I permute the variables, the polynomial should look the same, not evaluate, it should look the same. But in this context, it's essentially the same thing. So it will evaluate to the same thing because it also leads to the same thing, but you can also just ask that it evaluates to the same thing. So what Bhrushundi et al. Proved is that if you ask the polynomial is symmetric and it is a torus polynomial that approximates majority within low error, then its degree has to be square root n almost, which is like really large. But the catch here is the polynomial has to be symmetric. But even with this, one could hope to prove that okay, torus polynomials cannot approximate the majority function, because in many cases something called a symmetrization is known, which is, say you consider a real polynomial and a symmetric Boolean function, say they are closed as real numbers, then you just consider all permutations, take all these polynomials, take their average, and you will get a symmetric polynomial which approximates the same function with the same guarantee without increasing the degree. So now one might have hoped that okay, there is a symmetrization procedure for torus polynomials. Why not? Maybe there is. So first of all, does this work for torus polynomials? It cannot, because the integer parts can be different, and if you take the average of integers, it may not remain in. So it may actually create a random part. This technique cannot work, but maybe there is some other technique. And what we prove using this dual polynomial method itself is that there is no symmetrization that you can expect for arbitrary torus polynomials. So if you do not know anything about the torus polynomial and except for the fact that the function is symmetric, you do not know anything about the function, you cannot expect a symmetrization procedure. And the way we prove it is actually by proving that if a polynomial is symmetric, it cannot even approximate the AND function. This AND function was a constituent function for ACC0 circuits. So of course it has low degree torus approximations. But if you ask that to be symmetric, then the degree has to be really large. And in fact, this lower bound that we prove is almost tight, just away by some log factors. So as corollary, we get that symmetric torus polynomials are much weaker than their asymmetric counterparts. So this is kind of a negative result that you should take away, which is that okay, it's not enough to look at symmetric torus polynomials. We probably do have to look at asymmetric torus polynomials in themselves. So yeah, we also have some other results, like if you improve the error, if you ask for smaller error, you can get higher degree. And if you ask for even smaller error, you can get much higher degree, but only for the majority function for now. So some of the things that we are working on is like, okay, can we prove such a sliding scale lower bound that if you decrease the error even for the AND function, you will get a higher degree? And we expect that we can.
What
We have some
videos of that one was from
for just for the majority function. We want this to be for the AND function as well. And like some experiments suggest that this is actually true, but we are not sure how to prove it. Yeah, we would also like to prove some stronger lower bounds for the majority function. So something like, okay, you need degree to be almost n, but we do not know how to do this. We would also like to prove upper bounds using this method because it is possible. We do have some partial results in this, but not really worth mentioning so much. And of course, the ultimate goal is how we prove this for general torus polynomials.
Upper bounds and what?
So for example, we would like to construct something for the majority function using symmetric, but something like what Prahlad and Arkadev was suggesting already seems to work.
So this is false then? This conjecture may be false?
Oh, this conjecture may not still be false because we are asking for symmetric torus polynomial.
Okay.
So, but the upper bound might hold with respect to asymmetric torus polynomial. But the hope was to use this method to prove some other things. Yeah. So I think, yeah, so that's it. Now some questions or whatever. Yeah.
So, I mean, in your linear programming way of approaching it, I mean, like you were looking for, you're basically trying to disprove the existence of a torus polynomial by somehow making certain constraints work out. And the set of constraints you want to work out was a function of majority. Like for instance, if the number of things were at least more than half of it or something, in such situation, we want this constraint to work out.
Yes,
I mean,
yes.
That's roughly what it looked like.
Yeah. So actually, the problem here with like one of the conceptual issues we were facing with majority is that there is this dichotomy of entries being odd and entries being even.
No. So I want to ask a different question. Is that I don't want to deal with majority. Suppose I don't want to deal with majority.
Okay.
I'm just trying to see, is it possible for one to get a different proof of Ryan's theory by saying that, let's say all I want to show is that there exists a function which is in any XP, which is not approximable by your torus function. Right? So that will, I mean, like, so now you have freedom in choosing which sets you can.
Of course.
I was wondering if you, like, for example, if Ryan's proof already gives you something of that nature, or
unfortunately, we have no explicit function at this point for which any of this works. So we do not have any explicit lower bounds for torus polynomials. What we do know is that, okay, that's not very hard to see, but random functions are hard for torus polynomials. So that's always easy to see, but explicitly we do not.
Is it a concrete lower bound or is there diagonalization sitting inside?
It is diagonalization.
There is diagonalization.
Okay, so there is all of these approaches have been very concrete lower bound so far.
In some sense, it comes very close to proving a lower bound for torus polynomials. Yeah, because, I mean, in some sense, there's only one step, because, if I am correct, because the proof has this two things. One is this upper bound on ACC 0 by this mid-bit polynomial, which I think is at least as powerful as the torus.
Yes.
But then at some point, he falls back and again uses the fact that this function is again computable by a class of circuit which is closed under taking hands.
So the way,
That's the part that will break.
Okay.
so the thing is that,
It's a very subtle thing.
so like, his proof could have potentially worked for something like mid-bit plus or torus polynomial. But this step which first reduces the number of variables so that when you do exhaustive search, it actually requires less time. And when you do that construction, it gives you a mid-bit plus circuit on reduced number of variables, which then ends up taking less time. But if you have n number of variables, you have a mid-bit plus circuit on n number of variables, it will take 2 to the n time. So his algorithm does not save time for mid-bit plus circuits. It saves time for AC.
What are
I do not have
it's a bit.
yeah, so it's like this. The mid-bit function is that if you have n variables, you sum them up. You look at the sum as its binary expansion, log and bit binary expansion, and just output the middle bit. That's the mid-bit function. And now for mid-bit plus, what you have is inside a mid-bit, you are feeding AND gates of small parents. That plus.
Oh,
That's the plus.
now I see. So that's what you get from the Beagle derby.
Exactly.
Yes.
Okay. Yeah, I see.
But that's not going to be closed under that.
Yeah. Okay.
Yeah.
And I suspect because the similarly also.
Yeah, we do not know.
So I have one other question. So it seems like you extended the proof of the Bhrushundi industrial to
And function.
the ants.
Yeah.
So but ideally, at this point, you might want to say what happens if sort of and is allowed for free.
And is allowed for free. Okay.
Yeah, I know. So is there a way to do that? I don't know.
So in the world of torus polynomials, you suddenly want to introduce and as a free form.
But and is hard for symmetric, not for torus.
Oh.
It's hard for symmetric numbers. And it does come essentially for free for torus because you have like log square and degree polynomials for log and.
Oh, that's yes, no. I see. Only works for symmetric, only works for
Just to the symmetric, is there a symmetric polynomial for which there is a good asymmetric torus approximation?
Asymmetric function for which there is a good. So
I mean, no, there is a function is symmetric,
not symmetric
but there is an asymmetric torus polynomial that.
and function.
Oh, right.
Yeah. So that's why we are
that's
able to say that symmetric are much weaker. Yeah.
So there's Krishan who's asking, he's following on YouTube but unable to ask. So in this setting, when D, suppose you assume that D is a constant, then do you have a bound in such case, in a very special case?
For D being a constant, very simple arguments are able to work out. Like just by looking at what is the maximum value this polynomial can take, or that those kind of arguments easily work out. Yeah.
supposed to get a super constant lower bound.
Yeah, I mean, like what sort of bound can you get on this 2 norm or something?
Yeah. So in fact, for the AND function, for asymmetric torus polynomials, we are able to prove it requires degree log n.
Oh, right.
But yeah, so that's not really helpful because again, it's for the AND function.
More questions? Let's stand rather.
Repeat the solution.